I'm going to go ahead and help you guys get started on this. So these are slope fields. So there's some strategies for these problems when you're trying to recognize what is what. So if you look at the first section versus the second section, there's two different ways you can look at a slope field. So what I want you guys to notice is that the first section, they are graphing the slopes. So you can see dy dx equals x plus 1. So these are actually the derivatives. Does that make sense? These are the derivatives. And this is what you are graphing. All right. And then for the next section, you can see that the slope field, you are matching the slope field with the family of equations. They did not give you the differential equation. They gave you the family of functions. See the difference? Does that make sense? So you're not seeing dy dx equals, you're seeing y equals. Okay? So here we are given the differential equation that we're going to use to create the slope field. Okay? Here you're going to be taking the given slope field and you're going to be matching it with the family of equations that it represents. So these are two very different types of problems, even though they both have slope fields in them. Okay, slope fields can go for different types of things. So what we're going to do is I'm going to show you guys, you did the notes last night, so you've seen how to create a slope field, but we're going to practice it, just make sure that we have some strategies for maybe how to do this in an efficient way. Since these, I like to do these in marker, which is not erasable, so that can be dangerous, but I like to do it in something that sticks out on the paper so it's easier to see. It is up to you. If you have an erasable pen, that would probably be perfect. All right, so whenever I see dy dx equals something with just x's in it, then I know that the y coordinate, the y value, is going to have no influence whatsoever. Does that make sense? The y doesn't have any input. So that means that the columns, all of the x values, x equals 0, x equals 1, x equals 2, the x values are the only thing that matters. So the columns are the same. If we were doing a slope field that only was in terms of y, then all the rows would be the same because you'd have only the y coordinate would matter. So for this one, if we plug in an x value of 0, what is the slope going to be? 1. So if I plug in an x coordinate of 0, my slope is going to be over 1 up 1. So I'm just going to draw a slope of 1. Yeah, this one's nice because they have like nice little squares that are easy to draw. Okay. If we plug in -1, what's the slope going to be? 0. If we plug in -2, what is the slope going to be? -1. Okay, so those three are easy to draw. Okay, if we plug in 1, what is the slope going to be? 2. So this one's a little bit tougher to draw. Okay, if we plug in 2, what's our slope going to be? 3. Now make sure these two columns should not look the same. So you have to be really careful when you draw them. They should not look the same. Yeah, I'm not gonna count, but don't make me tempted to. And there are FRQs on differential equations where they do have you draw a portion of a slope field. They won't have you draw this many points. They might have you draw like 9 points or something. But you do have to be able to draw them accurately enough that you could tell a difference between your different slopes. Okay, so make sure that you can do a good job drawing those. Okay, so that's my strategy if I have just X's or just Y's. All the columns are the same, all the rows are the same. Pretty easy to draw? Okay. Now, when I have problems where there's X's and Y's that are interacting with each other, I like to find patterns that are going to make it a little bit easier to draw. So, for instance, if I had X plus Y, I would think about, okay, is there a way I can figure out where 0 would be created? So how would I find points where X plus Y equals 0? It's going to happen on there, right? Which X and Y coordinates are going to make 0? -1 and 1. So where is that going to happen? We're going to have it in the second quadrant, right? -1 and 1. 0 and 0. 1 and -1. So where is it happening? Yeah, it's on the diagonal, right? So do you see how there's still kind of a pattern? So you can still, even though it seems like it might not work with columns or rows, there's still going to be some sort of pattern that allows you to draw this in an organized way so that you can still draw good, correct slopes without being all disorganized and like haphazard about it. Does that make sense? Okay. If we look at ones like this, whenever they have problems where they are written as fractions, I like to look at what is going to make the bottom of the fraction 0 and what's going to make the top of the fraction 0, because that can help me draw some lines too. So let's think about what is going to make the bottom of the fraction 0. X equals 0. Okay, so let's look at what makes X equal 0, and then what types of slopes should we draw there? So X equals 0, is that going to be a vertical line or a horizontal line? It's going to be undefined slopes, okay? And that's going to be a column. We're going to have a vertical line of undefined slopes. Okay, so at X equals 0, we're going to do undefined slope, undefined slope, undefined slope, undefined slope, undefined slope. Does that make sense? Okay. Oh, we're going to do more. I just got you started.
Oh, okay, because I was like, do you have to touch every dot?
Yeah, no, you're right. You do have to draw a slope for every dot, but those are some strategies. And then those strategies also work if you're trying to match a differential equation with a slope field that's given. Then you can look and say, oh, it says X plus Y, so I know that I should look for that diagonal of zeros. Oh, there's an X on the bottom. I know I should look for vertical slopes. in that column. So you can start to recognize if you have a slope field that's given, you don't have to feel overwhelmed. You can look for key pieces that can help you narrow down what your slope field is. Does that make sense? Or if you're doing a multiple choice problem, you could start to pick out little pieces in the slope field that would make it easier for you to figure out which one it goes with. Does that make sense? Okay. If we put 0 on the top, what are we going to see? Y equals 0. So where are we going to draw that on the slope field? The x-axis is going to be slopes of 0. So 0, 0, 0, 0. Okay. All right, so I will let you guys work on that a little bit more. Now this one, these are the family of functions. So this means they gave you a specific function, but a family of functions means that these could have different initial values. They could have different starting values. And you can tell because like we've got sine graphs and cos graphs, and that could be, can you guys tell which letters look like the sine graphs and cos graphs? Yeah, I definitely looks like it. So I'm not quite sure which one it is, but you can see that it's shifted up and down. Does everyone see that? So depending on what your initial value is, you could have your initial value is like something like 1, or your initial value is something like 2 or 3 or 4, which would shift the midline of the graph up or down. Does that make sense? So you have a family of functions because a sine graph or a cos graph, they have that curvature where they go up, down, up, down, up, down. But you could have sine graph plus 1. You could have sine plus 2, sine plus 3, sine plus 4, sine plus 5. Those are all within that family of functions. Does that make sense? Or sine minus 1, sine minus 2, sine minus 3, sine minus 4. So that's why they're saying family of functions, because whichever of these curves you decided to trace, they would all actually be the same graph. Does that make sense? Or like this one over here has horizontal lines. So you could say y equals 3, y equals 2, y equals 1, y equals 0, y equals -1. All of those would be different families of functions. Does that make sense? Okay. Now keep in mind what you're actually seeing graphed. These slope fields, they were not created based on the y equals. They were created based on the dy dx. So don't say y equals 1, ooh, I can see y equals 1 right there, so g must match up with 2. That's not necessarily the case because y equals 1 did not create this. It was the dy dx that created it. Does that make sense? Okay. So let's go ahead and let's kind of think through some of these problems. So we'll start off with one that is maybe a little bit easier, so you guys can think about this a little bit. So think about, so I'm going to start off with h because this one is going to be a pretty easy one for you guys. So if y equals x squared, if that's the family of functions, then that means that dy dx, your differential equation, is what? 2x. Okay, so if we think about what that slope field would look like, all the columns would be the same. Does that make sense? All the columns would be the same because they're all in terms of x. And what else would we see? Uh-huh. Okay, so on the right side, we would see positive slopes. Okay, on the left side, we would see negative slopes. Okay, what else would we see? Where x equals 0, we would see 0 slopes. Okay, so where are we seeing that? What answer? 4. Okay, so let's look over at 4. So we see positive slopes, we see negative slopes, we see 0. And what you're going to notice is that if you look over here, if we were to pick any particular answer, let's say we had an initial value of -2. If you were to take these and lightly follow the slopes, I'm going to kind of follow it up there. What do you see? There's the function. Does that make sense? Now, if you see dy dx equals 2x, isn't it tempting to go with 3? It's very tempting, isn't it? Okay, but the shape of the parent function actually goes with answer 4, Roman numeral 4. You don't. You might be able to see the shape within the picture. Does that make sense? So there's kind of two ways to go about this. You can take the derivative to get your differential equation and think through how the differential equation would have created the slope field. And you can also kind of look for the picture of the function itself within the slope field. Does that make sense? So there's kind of some strategy involved here. All right, so we're going to say this goes with h. Let's try another one. Which other one do you guys want to try? Try C. Okay, what's the derivative of ln x? Okay, so does anyone remember what an ln x graph looks like? No. You're thinking of a 1 over x squared graph.
It's the Caleb version, but it's diagonal. Oh, I see what you're saying. It's like on opposite.
Okay, so what is ln the inverse of? What does ln cancel out? E. Okay, so let's draw.
It's this one.
Okay, so but we're going to talk through this because I think this is a good thing to be able to talk yourself through when you're taking a test. Okay, because every single one of you immediately said E. We all knew that, right? Okay. So here's a grid. So what do exponential graphs, because e to the x is exponential, what do they typically look like? Okay, so they go like this, right? Okay. What is the line that inverses are reflected over? Anyone remember, if you were to graph an inverse, what is the line that inverses are reflected over? Y equals x. Okay, so if you want to graph an inverse, you have to reflect it over the y equals x line. That's how you know with inverses you trade the y and the x. It's because they're reflected over y equals x. Okay, so if this is an exponential graph, then what does a logarithmic graph look like? Yeah, it's the other way. Like that. So we're looking for a slope field where you could draw something like this on it. E to the x is the inverse of ln x. So that's kind of a clue right there. Okay, so let's think about this. Let's think about what our slope field is going to look like. Our slope field is only in terms of x. so it's only going to have columns. Okay. What do we know about our columns? Or what would the slopes be if we had them? Vertical. They'd be vertical. So on the y-axis, the slopes would be vertical if we had them. So that gets rid of a lot of answers, doesn't it? Which answers does that get rid of? Okay, so 1, 2, and 3 are out. 4 is out because we already have that one. So we just narrowed it down to 5 or 6. And we actually already know the answer because we know what an ln graph looks like. So what's the answer? 5. And you can tell also, the other way you can tell is because this is positive 1 over x. And so positive x values should have positive slopes, and negative x values should have negative slopes, and that's the other reason you can tell it's not 6. So this one, so if we were to have, we're not going to have initial values that are on the x-axis, but we could have something like this. Right? There's your ln graph. The only way that you would have an ln graph over here is if you had an ln graph that had a negative inside, where they had a reflect over the y-axis. If they had a reflection over the y-axis somehow in the problem, that's the only way that you would get on the other side. So typically we see ln graphs over here, but it is possible to see them over here if you reflect over the y-axis. Okay, how do you guys feel about that one? We did one of the tough ones. Kind of makes sense. Okay, you guys feel like you could match those okay? We got those better? Okay. I just want to see if there's any other ones that I wanted to talk to you about. I think that was it. So, and that's kind of the gist of what you guys are doing today, is just getting more comfortable with these, coming at them from a variety of approaches. Okay? Sound good? The other sheet is just more of the same. It's just a punchline. Yeah, just matching.
Oh, so it's more like this number 5. Well, the second part.
Yeah. All right, go ahead and get to work.